Okay, hello again. In this session, I want to study and discuss the flow transition over smooth constriction. Okay, so imagine we have this constriction here. So this is a 3D view of that. Okay, uh, and then we have water. So we have this constriction where kind of this channel contracts here in the middle, and then we have water up to some elevation, say y1 at the beginning here. So we have some water that is kind of moving this is water, right? So we have some water that moves uh, along this constriction. Okay, so we can show it like this. Okay, so now we want to investigate what happens as the water goes toward this constriction. So this is a perspective view, a three-dimensional view, and here you can see a top plane view. So if you see it from top, this is what happens and what's actually the constriction looks like. So this is like you have this constriction that kind of from top view is kind of contracting, and then we have water that enters from here at section 1 with velocity u1, where the width of the channel is b1. Okay, and then as it goes further, the width of the channel changes as a function of x, where x is in the stream flow direction, and then it reaches the throat where the width becomes the smallest here, and then we again go back to the original width. So we want to see what happens as the flow moves through this smooth constriction. Okay, so we want to formulate the flow behavior based on different situations that might occur here. Okay, so the first thing I want to assume is that because I want to assume this is a smooth transition, so we assume that there are no energy losses. So there are no losses. So because this is a smooth transition, I want to say it's smooth, so it's not gonna suddenly jump like a hydraulic jump. So no hydraulic jumps. Because this is a smooth transition. So now the question is, as the flow or water passes through the constriction, what happens to the water depth? Is it going to increase? Is it going to decrease? As the flow goes over this constriction, what happens to the water depth, right? So the initial water depth is y1. You want to know what happens as it goes there. Is it going to increase or is it going to decrease? So this is the question we have. And we want to answer this question. So I will first start with writing the continuity equation. So continuity So I want to write continuity for this two sections, between sections 1 and 2, or between sections 1 and, let's say, this one, any arbitrary x. Okay, so if you write it down, it will be u1 times, because again we can assume it's a steady flow, so the partial over partial t term cancels or becomes 0. So we have u1 times a1. This is a flow rate. You can just, because the density is also constant, I can just write q1 equals to q2, which means, or qx, say, q1 equals to qx. So this means that u1 times b1 y1 equals to u at x, b at x, y. Okay, so b1 again is the width of the channel, and y1 is the depth of the channel. Okay, so I will put this back here. Okay, so this is continuity equation, and now I can also write Bernoulli equation. So I can write Bernoulli equation here. Unlike the hydraulic jump, since there are no losses, so since we don't have any energy losses. Okay, so what I want to do, I want to write the Bernoulli along the surface of that, because the pressure is going to be always the atmospheric pressure, so it's gonna cancel out. So along the surface, I can write it down. So Bernoulli is u1 square over 2 plus gy1, right, gz1, plus the pressure term, which is the atmospheric pressure, equals to, so I'm writing between section 1 and this section x, right? So it equals to u square over 2 plus gy plus p, again the atmospheric pressure because it's along the surface of the flow. And the atmospheric pressures are going to cancel out from both sides. They are equal. And instead of u square, okay, what I can do, I can write it in terms of u1 by. So we have from continuity u equals to u1 times b1 over b times y1 over y, right? We have it from here. Just look at it. This is from continuity. So instead here, I'm going to write it down in terms of u1. So I have one less unknown. So I have 1/2 of u1 square times b1 over b square times y1 over y square. Okay. Now I divide everything by gy1, so divide. So I'm gonna get this 1/2 u1 square over gy1 plus 1 minus, I bring this to the left hand side, minus 1/2 u1 squared over gy1 times b1 over b squared times y1 over y squared minus y over y1 equals to 0. Okay. So what is this? This is just Freud number, right? Freud number at section 1 squared. And similarly, this is also Freud number 1 squared. Okay. So now I multiply everything, the left hand side and right hand side, by y over y1 squared, and this is what I'm going to get. I'm going to get, and then I just rearrange the terms. I am going to get y over y1 square cube, so this is this term. Then I have minus, and just rearrange the terms, so you are going to get y over y1 squared 1, which is this term, plus this term, Freud 1 square over 2, plus this term, which is going to be b1 over b squared, and this term is going to become 1, times Freud number 1 square over 2 equals to 0. Okay. So now what did we get? We got a cubic equation for y over y1. In other words, this is like this equation, x cubed minus x squared, say, times a coefficient a, so I'm going to say coefficient a, x squared plus b equals to 0, where x is just y over y1, right? So this is exactly this equation. So I got a cubic equation for y over y1, and this cubic equation, like this one, this equation, has 3 solutions, because it's a cubic equation. So one solution is typically it's usually non-physical, so we can just neglect one solution. Typically, for example, is negative, right? So it's non-physical. So we have to solve this equation to get the exact solution, but what I want to do now is I want to look at the kind of the variation of y with respect to x, the stream flow direction. So I'm going to differentiate this equation that I got with respect to x. So I'm going to get, if you do that, you are going to get dy over dx equals to, and rearrange the terms, you're going to get this y over b Freud number square over 1 minus Freud number square db over dx, where Freud number is u over square root of gy. So you can differentiate it and rearrange the terms, and you're going to end up with this equation, which shows dy over dx, how the depth varies in the x direction, right? How this depth varies as it goes along this channel or constriction, okay? So now I want to investigate some behavior of this y, dy and dx depending, and this is the Freud number, right? Depending on the Freud number. So the first case is when Freud number is smaller than 1 everywhere in the domain. So when we have a subcritical flow everywhere, so we can have two situations. Situation 1 or condition 1 is when dB over dx is smaller than 1, is smaller than 0. What does that mean? This means that this b is constructing, right? So this b has to become smaller, this b has to become smaller. So in this situation, when dB over dx is smaller, becomes small, b becomes smaller as the flow goes in the streamwise direction. So this means that we have constricting or contracting. And so just put it in this equation. So we have Freud number is smaller than 1, okay? So this let's say, so this is smaller than 1, so this term is gonna be greater than 0, right? It's gonna be positive. This is also a positive number, Freud number. And then we have dB over dx, which is smaller than so this is going to be positive, and then we have dB over dx, which is here in this situation that we are investigating, this is smaller than 0. This is a negative term. So then this is dy over dx, so dy over dx should be smaller than 0 or should be negative, meaning that the depth of the flow has to decrease as it goes over this constriction. Okay? On the other hand, when dB over dx is greater than 0, meaning when dB over dx is greater than 0, like here, b is increasing, the width is increasing with respect to x, so this means that we have opening up in the channel. The channel is opening up. So in this situation, when your dB over dx is positive, then this term is going to be positive. So this term is going to be positive. So the whole dy over dx is going to be positive. Okay? So this means that the depth is going to increase. Okay? So I can put it here. So this is going to be positive. So the whole dy over dx is gonna be positive, so y is gonna increase with respect to x. Okay? So what happens is as follows. So for example, when we have contracting flow, I am showing it in from top view. Okay? This is top plane view, the plan view. So here when we have contracting flow with a flow number smaller than 1, a subcritical flow, y is gonna decrease, right? Here, from here we have it. This is converging, okay? And this is when the flow number is smaller than 1, okay? On the other hand, when B, or the flow width, the channel width is increasing with X, in other words, we have diverging flow. So this was converging flow and this is diverging flow, right? So dB over dx is positive, then y, the depth of the flow, is gonna increase with x. So we have here, as it shows it here. Okay. So if I want to show it from side view, it is as follows. So from side view, what's going to happen is like this. So we have flow here that starts with y1. So the depth of the flow, the initial depth is y1, right? Like here. And then as the flow goes over this constriction for flow number smaller than 1, the y has to decrease, so the y decreases. To say y2 in the throat, in the center. And then as it goes toward the diverging part, the width is increasing, the depth of the flow is gonna increase too. So we will have something like this. Okay, so this is from side view. This is from plan view, from top, and this is from side view. So this is how the flow, the depth of the flow is going to change in this constriction when flow number is smaller than 1. Okay, so how about when we have a flow number is greater than 1 everywhere? So let me write it down here. So 2, first was when flow number was smaller than 1 everywhere, and now flow number is greater than 1 everywhere. So similarly, you can do this and you will get when we have a converging flow, when we have the dB over dx is decreasing, now because flow number, I can write it here. The flow number is greater than 1, so this term is going to be smaller than 0. And this term is also smaller than 0. So now dy over dx in general is going to be greater than 0. So dy over dx is greater than 0, meaning that y is going to increase. Similarly, when dB over dx is smaller than 0, you can show that dy over dx is going to be smaller than 0, meaning that y should, sorry, why I wrote it like this. So y should, this should increase and y should decrease. Okay? So if I want to show it like here, so I have this constriction. And now Freud number is greater than 1. What I'm going to have is as this. So here in the first part, y is increasing, and second part where we have a diverging flow, y is decreasing, right? So this is converging flow and diverging flow. So what's going to happen is as follows. So we have y1 here. So the depth should increase until we get here to the throat. So this is y2. And then in the diverging part, the depth of the water or flow should decrease. Okay, this is how it looks like. Okay, so what happens if we have a critical flow? Now the question becomes, what happens when Freud number equals to 1? So you know, if Freud number equals to 1, and dB over dx is not 0, meaning that we have a change in the width of the channel, what we get from here, let's see. If Freud number is 1, then, and this is not 0, so this is not 0, so this is gonna be also not 0, right? How about this term? This is gonna be 0. This equals to 0. So you are dividing a number by 0, so you are gonna get infinity, which is impossible, right? So the depth should be like this. Suddenly has to increase a lot. So the only place this is feasible, the only way this is feasible is if dB over dx is also 0. So then at least we have 0 by 0, so we can get a number. So the only place possible Freud number equals to 1 is when dB over dx equals to 0, meaning that the width of the channel should not change, which is where, in this configuration, which is at the throat. So at the throat, you see, here at the throat, you see that dB over dx is 0, right? It's not changing. Here dB over dx is positive. Here is negative, but at the throat, it is just 0. Okay, so the only way, in the only place where throat number can become 1 is at the throat. Okay, so this is an interesting thing, because if we want to, this is very interesting phenomenon, because if we want to increase throat number, or similarly Mach number, the flow should pass through the throat. So here, for example, everywhere but throat number was greater than 1 or was smaller than 1. But if we want to increase throat number, say here, so we have this kind of channel where okay, so say we have a subcritical flow, throat number is smaller than 1, or similarly even Mach number, you can talk about it. And here we have we want to increase it to a supercritical flow. So we want to suddenly say make a subcritical flow to a supercritical flow. This has to go through this throat. So here at the throat, this is only possible if this passes through the throat, where throat number at the throat becomes 1. So we can design it such this, design a flow such this, so we can change a flow from subcritical to supercritical. So remember, this is the plan view, plan view. And if you want to show it from side view, this is going to look like something like this. So we have water here, it's a subcritical flow. It's going to decrease because throat number is smaller than 1, right? Throat number is smaller than 1, and we have a converging flow, so we are in this regime. So this should the water profile should decrease. But what after that? After that, throat number is greater than 1. We have a converging flow, so the flow should still decrease. You have it here, the depth of the flow. So we are going to have something like this now. So we will have something like this. It continually decreases. And here we have Y1. And here we have Y2. Okay. So remember now, with this throat and with this configuration, channel configuration, we can actually make a subcritical flow convert it to a supercritical flow without losing any energy. In the hydraulic jump, the hydraulic jump always converts a supercritical flow to a subcritical flow by losing some energy. But here, say if you want to do conversely, like opposite of that, we want to make a subcritical flow to become a supercritical flow. We cannot do hydraulic jump because of thermodynamic considerations, because we have energy loss in one direction, so we cannot generate energy in the other direction. So instead of that, we can design something like this channel where we make a subcritical flow to a supercritical without losing energy by a smooth transition. Okay, so let me quickly review what we learned today. So we started with, in this lecture, we started with hydraulic jumps. So we defined what is a hydraulic jump. Then based on the continuity and momentum equation, because we had energy losses in hydraulic jump, we cannot use Bernoulli. So we use continuity and momentum equation in the x direction. And by rearranging the terms, finally we found that the depths of the hydraulic jump, the depths of the jump, the flow after the hydraulic jump, can be found based on the upstream flow number condition according to this formula. And then we found that this hydraulic jump only occurs if the upstream flow number is supercritical and the downstream flow number is subcritical. So the flow jumps from a supercritical flow to a subcritical flow. And it increases its depth and it loses energy in this situation. Then in the second part, we talked about the flow through a smooth constriction, where now we are actually changing the width of the domain, so width of the channel. So in the previous cases, the width of the channel was constant, but here we are changing the depth of the channel. So we wanted to see what happens to the depth of the flow as it passes through this constriction. And we assumed that we have no energy loss, so we could use Bernoulli equation. So we used Bernoulli along with continuity equation. And this is the final equation we got. And we differentiate that with respect to x, and this is the final equation we got with respect to the changes in the changes of the depths of the water with respect to the changes in the width of the channel and flow number. So then we investigated this in different situations, in different conditions, when flow number is smaller than 1 everywhere, meaning that the flow is subcritical everywhere. So when we have a converging flow, the depth of the width of the channel is decreasing, then the y, or the depth of the water, has to decrease. And when we have a diverging flow, then the depth of the water should increase. So if you look at it from side view, this is how the water profile is going to look like. And when flow number is greater than 1 everywhere, we have an opposite behavior. So y is going to increase in a converging flow, and when the flow is diverging, y, or depth of the water, is going to decrease. And then we investigated what happens if flow number equals 1, and we said it's impossible everywhere except the throat. And said we mentioned we can use this type of channels to convert a subcritical flow to a supercritical flow, unlike the hydraulic jumps. Okay. So in the next lecture, I'm going to go through the shallow water equations, and we are gonna drive the equations for that, these kind of shallow water equations, the governing equations for that. and based on some assumptions about the shallow waters. Okay, thank you very much, everyone.